In this video, we're going to start taking a look at being able to perform an operation called factoring of polynomials. And essentially, factoring of polynomials is basically going backwards from the FOIL process or the distributive property. Just like numbers, that polynomials can be factored. So for instance, we know something like the number 24 can be factored into 6 times 4. And then 6 and 4 can be factored into 3 and 2, as well as 2 and 2. And so 24 would have the factorization 2 to the third times 3. And that's essentially what we're going to try to do, except we're going to do it with polynomials, right? Now, just like some numbers, such as 13, the only factors of 13 are 1 and 13, and that's a prime number. And there are polynomials that are prime. So we want to be cognizant of the fact that not every polynomial that we're going to look at has the ability to be factored. So let's take a look at a number of ways that we can start to factor polynomials, and one of them is called the greatest common factor. And the greatest common factor has two components. It's the highest number that will evenly divide all of the coefficients inside of the terms of the polynomial. And then it's also the lowest power of all shared variables within a polynomial. And so we're going to start by just factoring and naming the GCF from each polynomial. So we have a really simplistic binomial to start with, 10y or plus 45. And we know that the highest number that's going to be evenly divisible, or that evenly divides both 10 and 45, is going to be 5. And there's no shared variable. So in this example, the GCF is f. And what we're going to do is we're just going to divide each of the terms by 5. And we're going to stick a 5 on the outside. 10 divided by 5 is 2. We carry down the y. 45 divided by 9, or 45 divided by 5 is 9. Now, this is the factored form. And to check the answer, what we would do is we would distribute the 5. And to check, 5 times 2y is going to be 10y. 5 times 9 is 45. So we get the same thing we started with. That's how you can check your answer. A second example, we have x to the 6th minus x to the 4th plus x to the 3rd. Now notice that in the GCF for this one, there is no number other than 1 as coefficients, and the lowest power of all the shared variables is going to be x to the 3rd. So we have a 6, we have a 4, we have a 3, and we're just going to go ahead and pick the 3 for this one. And just like we did before, we're going to divide all the terms by x to the 3rd. We're going to place x to the 3rd on the outside. 6 minus 3. So remember the rule for dividing exponents is you subtract. So that's going to be x to the 3rd. We're carrying down the signs in between. So 4 minus 3 is x to the 1st. And we can just call that x. And then x3 over x3 is just going to be 1. And of course, if you don't believe your answer, you can distribute. Remember, when you multiply exponents, you're going to add with like bases. So that's x to the 6th. There's an implicit 1 in the exponent on the second term inside the trinomial parentheses. So that's going to be x to the 4th. And then 1 times x cubed, if we're doing this, is going to be x to the 3rd, which is exactly what we started with in the original problem. All right, so this is a check. And then this is our answer. Okay. Now, there are some examples where we have both numerical as well as variable coefficient or variable terms or factors inside of our GCF. So in this example, the highest number that's going to divide 15, 21, and 9 is going to be 3. Right? And then the lowest power of the shared variables is x. And we're going to divide everything by 3x. We're going to put 3x on the outside of parentheses. 15 divided by 3 is 5. Negative 21 divided by 3 is 7. 9 divided by 3 is 3. So I'm just copying down the numerical coefficients first, and now I'll take care of the variables. So x cubed divided by x squared is going to be, or sorry, x cubed divided by x is going to be x squared. X squared divided by x is going to be a single x, and then these x's in the last term are going to cancel out. And then this is our factored polynomial. And a couple final examples. The highest number that divides 14, 28, and 35 is 7. And then the lowest power of each of the shared variables between x is going to be x to the fifth. And then finally, there's a single y that divides each of those. And so our GCF, we're going to put 7x to the fifth, y on the outside. 14 divided by 7 is 2. 28 divided by 7 is going to be 4. And we carry down the negative. And then 35 divided by 7 is going to be 5. And then we just go ahead and subtract exponents, remembering that y has an exponent value of 1. And so 7 minus 5 is 2. And then y squared divided by y is going to be a single y. And then x6 divided by x cubed is going to be x cubed. Or I'm sorry, x6 divided by x5, can't read my own handwriting, is going to be x to the first. And then y squared divided by y is going to be y. And then finally, y to the fifth over, or x to the fifth over x to the fifth cancels, y divided by y cancels, and this should be our factored polynomial. And of course, if we don't trust that, we can go ahead and distribute. Finally, we have this 4x plus 5y minus 6c. And unfortunately for us, we look at 4, 5, and 6, and the only number that would evenly divide those is 1. And then also there's no shared variable. So for this one, the GCF is 1, which really means that this is a prime polynomial. All right, so there's nothing that we can do with this one. All right, so just making sure that you all don't get the impression that every single polynomial is factorable. Another way to be able to perform factoring is factor by grouping. And to be able to factor by grouping, this can be used if we have 4 terms. And there's other types that you might be able to factor that has more than 4 terms, but in this sort of section, we're just looking at being able to factor 4-term polynomials. So let's just take a look at a couple examples where we can factor by grouping. And what we're going to look for is a common binomial to factor out once we've done factor by grouping. So we have this 5x plus 15 plus xy plus 3y. And what we're going to do is we're going to group the first 2 terms. We're going to carry down the sign in the middle, and we're going to group the second 2 terms. Then what we're going to do is we're going to name and factor the GCF from each of the 2 binomials that we've created. So we know that the GCF between 5x and 15 is 5. The GCF between xy and 3y is a y. Right? And what I'm going to do is I'm going to write 5 and y on the outside of each of the parentheses. 5 divided by 5 is going to leave us with an x. 15 divided by 5 is going to leave us with a 3. Y divided by y cancels. Y divided by y cancels. And I want you to notice that we're left with the exact same binomial. Right? We have an x plus 3 as each of the binomials. What we're going to do is this is actually a GCF between these 2 terms. And what we're going to do is we're going to factor out the x plus 3. And if we factor that out, what we're left with is 5 plus y. Right? And this is sort of like if we were to go backwards from distributing the quantity of x plus 3 to each of those terms. And this is the way that you can check your answer, right? And so this is actually the final factor form. But if you were to distribute the x plus 3 to the 5, that would be 5 quantity x plus 3. And if you were to distribute the x plus 3 to the y, that would be y times x plus 3. And that actually gets us to this step. And then, of course, if we wanted to go backwards from that, we would distribute the y and distribute the 5 to both of those terms. All right, so if you ever want to check a factor by grouping, that's how you would do that. Okay. A second example of factor by grouping is we have 8w squared plus 7wv plus 8w plus 7v. And we're going to do the exact same thing. We're going to start by grouping the first 2 terms, and then we're going to group the second 2 terms. Right? Now, this one's a little bit different than the first one, but not by much. We know that there's a common w between the first 2 terms, and we're going to factor that out. And we'd say 2 minus 1 is going to leave us with an 8w. And then w divided by w just cancels, and we're going to leave up with 7v. And in the second set of parentheses, so this had a GCF of W. Over here, the GCF is going to be equal to 1. There is no number that evenly divides 8 and 7 other than 1, and there is no shared variable. So what I'm going to do is I'm going to stick a 1 on the outside of this second parenthesis, and clearly if you divide everything by 1, that just is an identity, and you're left with 8W minus 7V. Right? And so finally now we can do the exact same thing we did in the previous example, where we're going to go ahead and factor the common binomial of 8W plus 7V. Okay, so that's a GCF. So in one set of parentheses, we're going to put 8W plus 7V. In the other set of parentheses, we're going to have W plus 1. And of course, if you don't trust your answer, you can go ahead and distribute the 8W plus 7V to both W plus 1, and then distribute the W and 1 to both the terms, and you should get a 4-term polynomial that would represent the original problem back here. One last example of being able to factor one of these sorts of 4-term polynomials, we have 2x cubed minus x squared minus 10x plus 5. And this one's a little sneakier because now we have some negative signs in here. All right, so we're going to group. We have 2x cubed minus x squared, right? And then negative 10x plus 5. All right, now this is sneaky because if we were to just factor out a 2x or an x squared from the first term, and that's going to leave us with 2x minus 1. And again, all I'm doing is I'm just dividing each of these by x squared. And if I were to factor out a 5 from these two terms, that would leave us with negative 2x plus 1. And what we notice is that these two binomials are not the same. Okay, they look close, but the signs are flipped. Right? Here's the trick with these. An easy way that I've found to be able to factor these. If the third term is negative, here's the way that I do this, is I'm just going to go ahead and take that third term and just put a negative on the outside. In other words, I'm going to factor a negative GCF. Okay, so one thing to remember is if the third term is negative, okay, maybe try factoring the negative GCF from the second set of terms. Okay, so let's try that. So we're going to have a 2x cubed minus x squared plus negative 10x plus 5. Again, GCF here, x squared. And this time, we're going to factor a negative 5 from both of those. Okay, so let's give that a try and see if it works. So we put an x squared on the outside, and that's going to leave us with x minus 1, or 2x minus 1, excuse me, I forgot to drop down the 2. And then if we put a negative 5 on the outside, negative 10 divided by negative 5 is 2, and then we drop down the x. 5 divided by negative 5 is negative 1. And it looks like that works really nicely, because now we can go ahead and just factor out the common 2x minus 1. And then also we have an x squared minus 5 that's left over. All right, and again, one thing I would urge you all to do is to go ahead and distribute the 2x minus 1 to x squared negative 5, and then back distribute, or to distribute those two terms. So in the next video, we're going to take a look at how we factor differences of perfect squares, and then we're also going to look at how we factor trinomials.